Hi, and welcome to this second lecture in the computer security module. And for today, we are going to discuss and talk about authentication protocols. So what we will cover today, first of all, is a quick introduction to what an authentication protocol is. We will then discuss three types of authentication, which are going to be presented in the next few slides. And then we're going to talk about concepts such as message origin, authentication directionality, and key exchange protocols as a last concept that we cover today. So the reference for today's lecture is Modeling and Analysis of Security Protocols. If you remember from yesterday, I said that this book is slightly complex. It contains a deep way of looking at what a protocol is in using discrete mathematics notation. You don't need to understand everything, but as long as you can get grasp of the main concepts, that's good enough. Right, so moving on, first of all, we start with the question, what is a protocol? So if you are from a sort of computer networks background, you will have covered the idea of a protocol in your previous studies. So this is just to refresh your minds. Essentially, a protocol is a sequence of messages that are exchanged between two or more systems or people or entities or agents in order to accomplish a particular or a specific task or goal. Okay, so it's essentially a predefined or prescribed sequence of messages which takes place between two entities in order to achieve a particular task or goal. Now, a very famous example is the TCP sync exchange of messages, which happens between a client and a server. So the client sends a synchronization message to the server then, or the router, whatever it is, the switch, and then that device sends a sync acknowledgement message back to the client, and finally the client acknowledges the device's acknowledgement signal. So it's a three-step or a three-way handshake. We call it three-way handshake because it consists of three messages exchanged between these two entities. Now, essentially, there are various ways that you can define a protocol. Sometimes those ways are informal, just in plain English. Sometimes they are more kind of implementation oriented, perhaps in a particular programming language. However, probably the most appropriate way of defining a protocol is using some kind of a specification language. Okay, so that essentially renders the description of the protocol less ambiguous and more clear and more understandable, more understood among people who read it. So we call that a protocol specification, and essentially a protocol specification will define this kind of sequence of messages, and sometimes also it gives us, or most of the times in fact gives us also the format of the messages that are being exchanged. Okay, so we would like to know exactly what does each message contain inside itself. So moving on, we ask ourselves, okay, well, if that is what a protocol is, well, what is a security protocol then? Well, a security protocol is nothing other than a standard protocol, except that it has as its goal achieving some security related property. Okay, so it's like any other protocol, it's a predefined sort of sequence of messages. However, at the end of this sequence of messages, which will be exchanged between two entities, um, you end up achieving or establishing some kind of security property uh, or assurance for either or both of these two entities. Okay, so it's like a standard protocol, except it has basically it has security at its heart as the main goal, which is motivating the running of such a protocol. So we want to essentially establish some security property when we run a security protocol. Now, in real life, there are a lot of examples of such security protocols. Okay, so those range from things that we use very frequently in our, for example, Wi-Fi systems. So the WPA3 standard, also stuff that we use online on the web. So OAuth, SAML, and TLS, of course, infamously, or SSL, what we call it, SSL, and things that are a little bit more kind of akin for essentially IoT systems nowadays. Things like OpenID and OpenID Connect are also kind of examples of this sort of let's say security protocol. So they are um, quite heavyweight and complex, and that's because they attempt to solve a lot of problems at the same time. And therefore, you will find the specifications of these protocols or standards, we call them, running into tens and tens of pages, if not even hundreds of pages sometimes, because the protocol or the standard attempts to solve a lot of problems and accounts for a lot of contexts and environments. So we don't tackle these here. Instead, we will from now on, so in this lecture and the coming lectures, we will be dealing with small toy examples. Okay, and the toy examples allow us to essentially explain the security property or the security principle in an easy way that we can all understand without getting entangled into the complexities of an industrial standard like the ones you have on this page. So we said that a protocol was a sequence of messages, and then we said that a security protocol is a sequence of messages that attempts to achieve or establish a particular security property. But remember that we also said last time, we said that security is a very wide or general concept, and therefore it is appropriate that we break this down in terms of the simpler concepts or simpler properties underlying it. And we said that those were things such as authentication, confidentiality, integrity, accountability, and all sorts of more kind of specific definitions of security. And therefore, when it comes to the world of protocols or security protocols, it is also appropriate here to essentially kind of specify in a more focused way what we mean by security protocol, or what kind of specific classes of security protocols should we be looking at? And one of the most sort of popular such security protocols is the class of protocols known as authentication protocols. Okay, so what is authentication? We explained it a little bit last week, but essentially, the idea of authentication is that you end up knowing certain attributes of identity, okay, or of the origin of some entity, um, or whether that entity is a message user or anything else. Okay, so you'd like to know a certain attributes of the thing that you're dealing with or you're communicating with. It's very important property as it stands, because without authentication, it is nearly impossible to you know, achieve authorization and access control. Okay, so we will talk later on in the unit about access control, which is essentially giving authorized access to your resources to certain people or programs or entities. And without knowing those people or entities, or knowing certain attributes about them, it is impossible for you to achieve such a thing. So authentication is the basis of authorization or access control, and therefore it is a very important property that often is a starting point when you're trying or you're attempting to put a system together in your organization. So as such, we can define an authentication protocol as a particular class of security protocols that have in mind a sort of achieving this property or some kind of type of authentication properties. So that leads me to the next slide, which outlines three major types of authentication that we will be covering here. And these are known as aliveness, mutual communication, and message agreement. So these are essentially three, let's say, flavors of what we call entity authentication. Okay, so they are three types of authentication which are related to the entity you're communicating with. Okay, so assuming you are a person and you're talking to another person, so these could be three ways of sort of authenticating them. Or if you are a system and you're or a client and you're talking to a server, again, these could be three ways of authenticating that server. However, there is also something we call message origin, and the idea of a message origin is sort of more related to the uh, data that we're receiving. Okay, the information, the messages that we're getting from somewhere. So basically, it's a property more relevant to the data or messages rather than being a property of the person or the system that we are talking with. Now, let's say we would like to understand what is the basic setup for an authentication protocol. So, like in any other protocol, we want to understand who are the major players. And in this case, we have four major players in an authentication protocol. So first of all, you have the two communicating entities, and often we call them Alice and Bob. Okay, so the assumption here is that Alice and Bob are two honest agents that are basically attempting to achieve or to sort of run some kind of authentication protocol in order to achieve a certain flavor of authentication. So sometimes they can communicate just between themselves directly, but also there are other occasions where they require the help of a trusted server. Okay, so the trusted server is a third party entity which basically will help both Alice and Bob in going through the protocol, for example, by either issuing keys or decrypting or encrypting certain messages or rerouting certain messages and so on to either party. Okay, but nonetheless, it is a trusted server or a trusted entity, meaning that it's got a role in the protocol itself, an honest role that is going to play in the protocol. So these are the three entities that will carry on in an authentication protocol. By contrast, you have something called an intruder, and this is your network, your untrusted network, which we call it sometimes the intruder or the attacker, and their role is to disrupt and basically attack your protocol in order to break down its properties or break down its communication, and therefore ending up with sort of either maybe stealing secrets or assuming incorrect roles and so on. So we will come to the idea of an intruder later in this module when we talk about attacks on security protocols. For the moment, we are kind of just going to be sitting within this box here, so we will assume that everything is normal and ideal, and therefore, we're not looking at attacks at this stage. So let's recap here the main building blocks for our messages. And this slide is just to sort of lay down the terminology, lay down the language that we're going to use from now on, and the various symbols that we're going to utilize in sort of building up our protocols and writing them down. So as we said, and we came across these last week as well. We said, first of all, we said that an encryption essentially looks like this. So basically, you have a message written between two curly brackets, and then followed by a key. So this implies that the message is encrypted using the key K. Then we talked about as well, last time we talked about digital signatures. So in this case, digital signature is written in the following way. Basically, we write the message M between two curly brackets and a vertical line. Okay. And then we have here followed by the key, some kind of private key, KPR. Okay, so that implies that the message M has been signed using some kind of private key, KPR. Then a hash function is simply letter H applied to message M. Okay, so that means that the message M has been hashed by whatever this hash function is, whether it's MD5, SHA, whatever. Then we said we also have composition of different items that we put together. Okay, and remember we used the comma symbol for that last week. And basically, composition allows us to create what we call tuples. Okay, so tuples are like pairs, except their size is more than two elements. Okay, so essentially, you have all these elements are in a tuple. So you have M1, M2, and all the way up to Mn. So this is essentially an n size tuple. Then we will encounter some other elements. So we have something called a nonce, okay, and a nonce is a number that you only use once, okay. So it's like those kind of one-time passwords, okay. So we use the symbol N or the letter N to denote nonce. You have a timestamp, and the timestamp is the time which is attached to your data, the time of creation, for example. So if you were looking at your file, every file has a timestamp, and we use the letter T to denote a timestamp. Then we have names of agents and entities that are participating in a protocol. So those are the Alice, Bob, the server, Carol, whoever it is, Dylan, and so on. And we use the capital letters A, B, C, D, and so on to refer to those agents. We reserve the letter S always to refer to that sort of trusted third-party server. Okay, and finally, the last entity or last building block in our language is standard text, okay, or strings, or they could even be numbers, for example. So hello world, or 1 2 3 4 5 6, whatever it is. So these are all kind of any sort of basic data, whether it's strings, numbers, anything else, is also forms part of this language. So this is the example that we're going to use for the rest of the lecture. So this is a protocol example. You have Alice A and Bob B here attempting to communicate using a third-party trusted server in the middle. And basically, the protocol is a two-step communication, meaning that there are two messages which will be exchanged in this communication. The first message is sent by Alice, and that message contains Alice's name and the encryption of three things put together. Well, strictly speaking, there should be this should be a tuple. So I really should have put, let's say, a bracket here. Okay. What are these three things? You have, first of all, a timestamp created by Alice, then you have B's name, and you have a key which is being proposed by Alice for communication with Bob. And the whole thing is basically encrypted using the key that Alice shares with the server. So when the server receives this message, remember from what we said last week, that the key is, if the key is basically shared between two entities, they can both use it for the purpose of encryption and decryption. So in this case, the server will simply look up in its internal database and for the key that it shares with A, and it will therefore retrieve that key KAS. So then it'll basically take that key and use it to decrypt this whole thing here and release its internal content, okay, which is basically the timestamp, B's name, and the key which Alice is proposing for future communications with Bob, which is KAB. Now, once it's done that, it will naturally then respond with a message that it will forward to Bob. Okay, so I'm just trying to repair this missing, these two missing brackets here for the tuple. So that message contains a timestamp from the server, Alice's name to say that this message is coming from Alice, and that key that Alice has proposed for communication with Bob. So it takes these three things, composes them together in one tuple, and it then encrypts that tuple using the key that the server shares with Bob. Okay. So when Bob receives this message from the server, it will essentially pull out that key from its internal database that it knows it shares with the server. So it'll pull out the key KBS, and then it'll use it to decrypt the message and release the internal content. So it'll look at this, B then, or Bob will then look at this content, and it'll see that this is basically the server telling Bob that Alice would like to communicate in the future with Bob using this particular key KAB. So what will happen once this protocol has been completed is that Alice and Bob can then exchange any sort of secret or sensitive messages with each other using the key KAB. Okay, and basically, once they've run this through this protocol, they've got that shared key together. What I've done here as well is that I've put the scopes of the keys just so that you remind yourselves who sort of knows which key. Okay, so in this case, for example, KAB will be shared between A and B, whereas KAS is shared with A and S, and KBS with B and S. Now, there's something else often we say about such keys, which is their duration or for how long they are basically valid. Often keys that are already used from the beginning is something we call long-term keys. Okay, so the keys that you share with the server, for example, imagine your password. These are long-term keys. So they last, they're always there. You can change them you can update them from time to time, but they have long life. Okay, so they last for a while. On the other hand, keys such as KAB is something that we call a session key, and that means essentially that they have a short validity that lasts only for the duration of one session. Okay, so you run through this protocol, you establish the key, you can use the key, but once you have finished your communication, for example, you've shut down the computer, or you've logged out from the website, or just you've walked away and you've been inactive for a while, then you need to rerun the authentication protocol again. So once you rerun the authentication protocol, the previous key that you've established, KAB, becomes invalid, and basically your new run of the protocol will establish a new session key, KAB prime, let's call it, for example. So that's the running example that we will be using, and now we move on to discuss the three types of entity authentication that we referred to earlier. Okay, we start with first type, which is known as the aliveness property. Okay, so aliveness property essentially is the simplest form of authentication that you can achieve, and it requires only that an agent is detected to be alive and running in some protocol session. Okay, so suppose I'm sort of trying to talk to you. Um, I don't really need any other assurance other than that I know that you are sort of alive and running at the other end of the protocol. That's the most simple, most basic property. So notice also something else is that in all these forms of properties that we discuss, they only always hold when the protocol terminates. Okay, so we sort of never kind of state anything, any property or any sort of, or we don't make any conclusion unless the protocol itself has completely terminated. If it hasn't terminated, it means things are not stable yet, and therefore we can't make any assertions out of them. Okay. In this case, in the case of the aliveness property, the idea is that when B terminates, the question is, was A alive or not? Okay. So let's take the same example that we have gone through in the previous slide. And we have Alice, Bob, and they're trying to communicate with the server via those couple of messages, right? So the question here that arises is, can the server know when it terminates that A was alive? And can the server know when it terminates that B was alive? And can A know when A terminates that either the server or B was alive? And finally, can B know when B terminates that either the server or A were alive? Okay, so the question here is, for either of these three entities, can any one of them basically know that the other two were alive when that entity terminates? And first of all, it might sound like a simplistic question, but it really isn't, because in this case, you know if somebody is alive or not only if they talk to you. Okay, so if you receive something from them that assures you that they were that person or that entity, then you know that they were alive when you were communicating with them. On the other hand, if you don't hear anything from them or you didn't receive anything that essentially proves they are who they are, then there's no way for you to know that they were alive when they were participating in the protocol. So let's try and answer these questions. So we start by the server. So did the server know when it terminated that it was talking with A? The answer is yes, because A communicated a message to the server that the server was able to decrypt using the key that it knows definitely came, or it's definitely shared with A. Okay, so it definitely then knows that it was talking to A by the time the server terminates at this point in time. However, can the server know that when it terminates that B is alive? The answer is no, because actually B does not say anything in this protocol. Okay, so even though you're sending B a message, there is no way for you to know that B exists. Okay, so therefore there's no way for the server to know that B exists, and therefore it can't tell whether it was alive or not during this protocol. Now, can A know when it terminates that either the server or B is alive? And the answer is no. The reason is because A talks to the server and doesn't talk to B at all. But on the other hand, the server never talks back to A, and B never talks back to A either. So the answer to that question is no. and no, because neither the server nor B send A any messages that prove that they came from the server or from B. And finally, can B know when it terminates that either the server or A were alive? And the answer is yes and yes. It knows that the server is alive because it receives a message encrypted with the server's key. Okay, so it knows that this message could not have been encrypted by anyone else other than the server, simply because that key is only shared between B and the server. On the other hand, it also knows indirectly that A was alive because that message, that whole message here, would not have been sent by the server unless the server received the earlier message and the server then was able to determine that that earlier message indeed came from A or from Alice. Okay, so by indirect sort of deduction, we can make sure, or B can make sure, that Alice was alive and participated in the protocol simply because as a result of that message there arriving at the server and being then decrypted successfully, the server was able then to transmit or send this second message to Bob. Okay, so as you can see here, sometimes in order for you to answer these questions, you need to follow a kind of indirect way of deduction or of sort of reasoning. So sometimes we can answer it directly from some message that we receive straight from that entity, but sometimes we have to link a number of these messages together in order for us to make the right conclusion. So the answer to the last question is yes and yes. Now, notice here as well that I use the word prove, okay, so that some entity can prove the existence of some other entity, and often that means that we have to be relying on the power of cryptography to be able to prove that someone did something or that someone indeed did send some message. So in this case, the server was able to prove that the message came from A, not because A stated that the message is coming from A, okay, so that's not the reason. The reason is because the server, when it used the key that it shares with A, that key was successful in decrypting the message that A sent it. Okay, so as a result, the server was then able to prove that A indeed was the one who transmitted the message, and therefore later, of course, as a consequence, that A is alive. Okay, so that's what aliveness is and what we mean by the idea of some entity being alive as a first sort of concept of authentication. Now, moving on from that, the second concept of entity authentication is known as mutual communication, and mutual communication builds on top of aliveness by adding an additional requirement. And this additional requirement is that you know that you're communicating with each other. Okay, so you know precisely who you're communicating with. So the idea here is that when B terminates, the question is, was A alive? And second thing, was A aware that it was communicating with B? Okay, so I don't want to know that A was alive only, but they actually A really intended to communicate with myself, okay, and that it wasn't actually trying to communicate with someone else. So going back to our example here, The question is, when B terminates, can B be sure that it was talking with A? And furthermore, does A believe it was following a protocol run with B? And the answer for the second part is dependent, of course, on B using the second session KAB. Okay, so the idea here is basically that since the since since B received the message from the server could not have sent this message, okay, this second message, unless it was successfully able to decrypt this or the second part of this first message. But the fact that the server managed to decrypt this first part of the message also tells us what the content was, okay? And the content here is clearly stating that A is attempting to communicate with B, and therefore that is the reason why the server selected B as the destination for its second message. And so therefore that means that A indeed is sure that it wanted to talk to B. Okay, so B knows that A was alive, but now B also is sure that A indeed knew that it wanted to talk to B. Okay, so it's an additional requirement that is added on top of the aliveness property. Now, finally, we have what we call the message agreement property, and in this case, it's an additional requirement on top of the mutual communication property, which states that not only you must be sure that the other side is alive and that the other side knows it's talking to yourself, but also that you two end up agreeing on some common data, okay, or some shared data. Often that shared data will be some kind of key that you use in future communication. So back to our example again, we see that indeed both entities end up sharing the key KAB. So KAB originated from A, therefore A has a copy of it, and finally it arrived at B, and so also B has a copy of it. Okay, and that's on top of the previous two properties that we established: the aliveness of A and the mutual communication with A that B managed to establish in the previous two uh, sort of properties that we discussed. Okay, so or the requirements. So this is a third requirement that adds on top of it, which says that you also must end up with some kind of shared data, and often, as we said, that shared data is the session key that you're going to use once this whole protocol is finished. You're going to use for your future communications to exchange hidden or sensitive messages. Right, so those were the three kind of flavors of entity authentication. So they are entity authentication related concepts because they tell us something about the other side that we're attempting to talk with, okay, or that we're actually talking with. So that's very important because they're properties of the other side of communication. They're not properties of the things that we're receiving, of the messages or the data that we're receiving. And for that type of properties, we call them message origin. Okay, so that's something that we want to understand is whether or what the origin of a particular message is, for example. And that's related again to authentication because you will want to know, and sometimes, just where did this message arrive from? Okay, so that is again a form of authenticity of the data or authenticity of the information that you're receiving. So if we look at our previous example, the question would be, let's say, whether the server knew that this what the source of this first message was that it received. Okay, and the answer is yes, it does, because it knows that no one else could have encrypted that message other than Alice, because simply it's encrypted with the key KAS. And another question would be whether B knows the source of the message that it receives. Okay, what is the source of this message? And the answer is yes, it does, because again, when it decrypts this message using the key KBS, it knows that this key is only shared with the server S, and therefore it knows that this message could not have originated from anywhere else in the world other than from the server themselves. And of course, you can break down that question into the further subparts of your message. So you can ask, what's the origin of this timestamp? What's the origin of this name, this key? Oops, sorry, and so on. You can repeat the same question for the subparts of your messages, and that is down to your requirements. Exactly, you know which parts do you want to be sure they're authentic, and which ones you don't. So, but that's in a nutshell is what message origin is. Now we move to another concept, which is authentication directionality. And if you noticed, sometimes we said that Bob is sure of the authenticity of Alice, okay, or is sure about certain properties about Alice's identity, and in that case, we didn't say that the other way around was true. Okay, so we didn't say that Alice was sure about Bob's identity. And that's very important because it gives us this concept of the directionality of authentication. That if you establish authentication in one direction, that doesn't imply that it is true for the other way around. In general, you have authentication protocols can be split in naturally in two classes. One is what we call one-way authentication, which means that one of the entities participating will end up knowing something about the other entity, but not the other way around. And two-way authentication, which means that both of them will end up knowing um, certain properties about the other side participating in the protocol. Okay. So one way, there are some protocols that are one-way authentication and some protocols that are two-way authentication. So here is an example of a one-way authentication protocol. It's a five-step protocol or a five-way handshake in which Alice and Bob are talking to each other, and they're doing so with the help of a trusted third-party server. Okay, so the protocol starts with A transmitting a message to B saying, hi, I'm A, and my name is A, I'm Alice. Then Bob replies with a number, some kind of unique number, which is a nonce that it generates. Okay, so this is NB. Okay, by the way, this NB here does not reveal anything about B's identity. It's just simply a number. The fact that we transcript it with the um, letter B is just purely to say that this was created by B, but it does not actually include B's name in it. Okay, so just be careful of that. And once Alice receives this number, it will then encrypt it with the key that it shares with the server and sends it back to Bob. Bob then takes that encryption and includes it in a pair of messages along with Alice's name, and encrypts that pair with the key that it shares with the server. When the server receives this this whole encrypted message, it will use the same key KBS to decrypt it. Then it will use the key KAS to decrypt the internal nonce and reveal it. And once it's revealed the internal nonce, it will then encrypt it using the key that it shares with Bob and send it back to Bob. So once Bob receives this whole message, it'll use the same key KBS to decrypt it and reveal NB. Okay, so NB in that case should be the same as the NB that it sent to Alice initially. Now, this is a one-way authentication. Why? Because in this authentication, basically, Alice um, provides enough information about herself to both Bob and the server for Bob to be sure that it was talking with Alice, but not the other way around. Okay, so notice here that in fact Alice has no way of concluding that it was talking with B. There's no way for Alice to conclude that it was talking for B with B, simply because B never actually sends any messages to Alice which sort of reveal anything about its identity. Okay, the only thing that it sends to Alice is this nonce here, which is just simply a number. Okay, and that could have been sent by anyone else. So it doesn't prove that it was B communicating with Alice. On the other hand, because Alice encrypts this message here with the key that it shares with the server, and because the server was able to decrypt that key and release the nonce, which then it forwarded to Bob, Bob is then sure that it was communicating with Alice, because no one else in the world has access to that key other than the server and Alice themselves. So as you can see, it's a one-way authentication. B knows that it's talking to A, but A has no idea uh, what the identity of B is, other than that there is some kind of someone here that it's talking with, and that someone has forwarded to her a nonce, and that's the only sort of conclusion that A can achieve. Now you'd wonder where in the world we have one-way authentication. That's very simple. If you look at your SSL, the everyday HTTPS thing that you do, that's a very famous example of one-way authentication protocols. You authenticate the server, i.e., you know the identity of the server that you're pointing your client page at, or your client software at, but not the other way around. Okay, so when you look at I don't know, BBC or any other web page, you know that you're looking at BBC, but BBC has no idea who you are. Okay, so it's a one-way authentication where one entity knows the identity of the other, but not the other way around. On the other hand, you do have also things like two-way authentication, and this is here a simple example of a two-way authentication between A and B. And we achieve this two-way authentication by using asymmetric cryptography, and basically we encrypt using using the public keys of the other side. The fact that in this case, when Alice sends the encryption to Bob, the fact that Bob is able to decrypt this message and then forward back the nonce back to Alice in the second message tells Alice that it must have been Bob at the other end. And the reason is because only Bob can actually decrypt this message. No one else can do that in the world. And similarly, the same thing happens. So Bob here sends his own nonce or number, unique number, to A, and because A is able to decrypt whole this whole message, essentially that tells Bob, when he receives the third message, that Alice was able to decrypt this whole thing here. And Alice would not have been able to decrypt it unless she had access to her own private key that matched the encryption using this public key for Alice. So by combination of these public and private keys, both Alice and Bob are able to essentially arrive at the conclusion that they're talking to each other, and this is what we call two-way authentication. Now, here's a thought for you guys. How do you achieve a two-way authentication using just one-way authentication protocols? If you think of it, the answer is very simple. You run the one-way authentication twice. Okay, so you run two instances of a one-way authentication, each time in a separate direction. Okay, so you run it once from A to B, and you run it the second time from B to A. Okay? And that way you can achieve two-way authentication using one-way authentication protocols. Right, finally we come to the last type of protocols, which are called key exchange or key agreement protocols. And these are not, strictly speaking, they're not authentication related, but they're often used in the context of authentication protocols. The idea of a key exchange or key agreement protocol is that you end up agreeing a secret shared key with the other entities. So remember, when we talked about, in our example, we talked about the two entities sharing up this sort of key at the end of the protocol. Well, sometimes the only thing we want to do is just establish a key, a shared key with the other side, but nothing really else. Okay, I don't care who you are. All what I care is I want to end up having a secret key with you, and that sort of classes of protocol is known as key exchange or key agreement protocols. The most infamous example for these is Diffie-Hellman. Diffie-Hellman protocol allows two entities to establish a shared secret without anything else. Okay, simply the way it works is that A and B first have access to two public prime numbers. Let's call them P and G. And essentially A has its own secret number called X, and B has its own secret number called Y. So the Diffie-Hellman protocol is a three-way exchange of messages, which starts as follows. First of all, A sends to B the two prime numbers. Okay, so just to say to B which two prime numbers we're going to use. Now, then A performs the following computation. So it takes one of the two numbers, G, and raises it to the power of its own secret number, X, and does that modulus the other prime number, P, and sends that to Bob. Now, when Bob receives this bit here, it's going to do something internally, which I will describe next. But at the end of it, it will also send its own computation, which is basically G raised to the power of Y modulus P. So what happens is that the two entities A and B exchange two numbers which are computed in these two ways. Okay. But these two numbers have a very interesting property, which is that if you perform the next computation on them, i.e. if you raise them to your own secret number modulus P, you end up with exactly the same number as the other side has computed. Okay, so when B receives message 2, it will take that number g to the power x modulus P and raise it to its secret number y to the power of its secret number y modulus P. And the same thing when A receives the last message, A will take the number that B has sent it and raise it to the power of its secret number x, then modulus P. Now it turns out that these two calculations are exactly equivalent. Okay, so they basically yield the exact same number. And furthermore, what is interesting is that just by communicating this partial computation and this partial computation, you cannot, if you are observing these two numbers, you cannot actually conclude or compute either of these two things because you require the two secret numbers that A and B have in their own system or locally. So this is something we call Diffie-Hellman. It's very widely used, very well known sort of protocol, and it represents common example of this class of protocols known as key exchange or key agreement protocols. That's all for today. Thank you very much for listening to this lecture. Goodbye.